So did you guys see the email I sent you? You saw that, right? I posted the notes on Brightspace, and I wanted you to work on the last questions, the set of questions. That was actually my plan for today. Tell you briefly about all these things which we already learned in our previous classes, and then going to do all those questions. Any question before you start? Any comments? So I realized that 3.2, section 3.2, whatever we talked in section 3.2, 3.3 and 3.4 are the same thing. The difference is in 3.3 and 3.4, they talk a little bit details than in 3.2. So since we covered 3.2, basically we covered the entire chapter 3. So it's a brief discussion before we do all those questions. Linear independent. So we say a bunch of vectors, they're linearly independent if they are not, if you cannot write them as a linear combination of one another. In other words, if you have a bunch of sets like bunch of vectors like v1 to vn, in order to see the formal definition says they will be independent if you have a bunch of coefficients, and if you multiply all those vectors with the coefficients and add them, the result is 0. It means it doesn't matter what you do, the linear combination is 0. And geometrically, what it means is that two vectors are linearly independent if they're not parallel. Parallel lines, they are independent of one another. Or one line, multiples of one line is linear independent, not linear independent, because one line is a multiples of the other line. So how do you know whether a bunch of lines, they are linearly independent or not? There are 3 ways you can check linear independency. The first one is easiest, but it requires to be a square matrix. So if you have a set of vectors that gives you a square matrix, then all you have to do is find the determinant. If the determinant is not 0, then they are linearly independent. But let's say you don't have a bunch of, you don't have square matrix. You have like 4 vector in R3 space, means it's 3 by 4. Then you have the third method. But if you have only 2 vectors, your life is easy. All you have to do is check if you can find some common multiple, and one vector is a multiple of the other vector. So 2 vectors is the easiest life. All you have to do is look for if they are a multiple of one another or not. If you have 3 vectors in R3 space, or 2 vectors in R2 space, or 4 vectors in R4 space, then they're square matrix. So look for their determinant. And if you don't have square amount, then all you have to do is find some, multiply all the vectors with some coefficient, and then solve your matrix system of equation by a reduced to echelon form, and then see if all the constant is 0. So when you multiply all the vectors with some type of constants and try to reduce them, if you realize that all the constants end up being 0, then they are linearly independent. Otherwise, they're not. Okay, so depending on what information you have, we have 3 ways to figure out linearly independency. And this is the most important thing for the rest. Spanning set depends on that. Basis depend on that. Dimension depend on that. So everything else depends on linear independency. So if you understand linear independency well, that means you can do the next 3 things. The second next thing after linear independency is span. A set of vectors span the vector space. If every vector in the space can be expressed as a linear combination of the vectors in the set. In other words, the span is the mathematical term for how much of the space you can cover using the vectors you're given to you. It measures how far you can get by using all the different ways you can mix and match those vectors. Like if you have Did I mention it here? Yes, the next one. If you have only one vector that is independent and the rest, it doesn't matter how many you have, but they're dependent on that independent vector. So if you have only one independent vector in your set, that means the span of that vector, it means how much one vector can cover in your space is just a line. But the vector has to be non-zero. If you have a zero vector, its span only is zero. It's span only a point. Okay. So if you have a non-zero vector, then that vector, doesn't matter what you do with that vector, you can multiply many other constant, and then get many other new vectors. It doesn't matter. The only thing you can cover in the entire span, in the entire space, is just a line. So one vector can cover only one line. So span of one vector, it doesn't matter on which space you are in, R2, R3, R4, it doesn't matter your dimension of your space. If you have only one linearly independent, the amount of space it can cover on your space is only a line. And non-zero vector, okay? Now, if you have two non-zero linearly independent vector in R2 space, it means on the XY plane, you have two linearly independent vector. That means those two linearly independent vector can cover the entire XY plane. However, if you are in 3D space with two linearly independent, they cannot cover the entire space. They can only cover two-dimensional plane. And it's two-dimensional plane because the XY is a two-dimensional plane, XY plane. So it doesn't matter which dimension you are in, either R2 or R3 or R4, the dimension of your space doesn't matter. If you only two linearly independent vector, the result or the amount of space it can cover is a plane, an XY plane. But if you have three linearly independent vector in 3D space, it can cover the entire 3D space. So span of three linearly independent vector in R3 is entire space, entire 3D space. That's why linearly independent vectors are very important. They tell us how much we can cover using those two vectors.
If there's four or more linear independence, is it just still 3D space?
On which space?
What?
On which dimension? R3, R2, R4, which one you're talking about?
No, if there's more than like if the span of like four linear independent vectors.
In which vector space? Are you talking about R4 or R3?
Like R4.
In R4, if you have four linearly independent vector, it covers the entire R4 space. However, it cannot have four independent vector in R3 space. Rn can have only n maximum linearly independent vector. So R2 can have two maximum independent vectors. R3 can have only three maximum three independent vector. R4 can have maximum four independent vectors. If you have more vectors than your dimension of your space, one of them definitely has to be dependent on the other three. Shibu?
That's what I was gonna ask.
So if you have three vectors in R2, okay, R2 means you have only X and Y value. So two rows. You have three vectors, but your space is R2. Third one or one of them has to be a linear combination of the other two. You cannot have more vectors than your dimension of the space. Dimension means R1, R2, R3, those things. The 2, 3, 4, those are the dimension of your vector space. So dimension of the vector space is in which dimension, number of linearly independent vectors is same as your dimension of your vector space. R2 can have maximum 2 independent vectors. R3 can have maximum 3 independent vectors. R4 can have maximum 4 independent vectors. If you have more than those, they are not independent. Okay, so how do you know whether a set of vectors is a spanning set for the vector space? It means the set of vectors they give you, do they span your entire space? How do you know that? Well, that's easy. All you have to see is, do you have n many linearly independent vectors in your Rn space? That's all you have to see. If you have 2 linearly independent vectors in your R2, there is a spanning set. If you have 3 linearly independent vectors in R3, it's a spanning set. You may have more than that, but you have to have at least n many linearly independent vectors in your Rn space. So spanning set requires independency and numbers. The m and n many vectors, they have to be same. You can have more, it doesn't matter, but you have to have at least n many independent vectors in your Rm space. Now, dimension of the span. So I talked about dimension of your vector space. Now, what is dimension of the span? Dimension of the span means how many independent vectors you have in your span. Okay. This is not the same as dimension of your vector space. Your vector space could be more, but the dimension of the span could be less. For example, you may have 2 independent vectors in R3 space. So the dimension of your vector space is 3, but the dimension of your span is 2. Why? Because you have 2 linearly independent vectors only. So dimension of the span means how many independent vectors you have. And definitely it has to be less than or equal the dimension of your vector space. It cannot be more than that. Like, you cannot have 4, the dimension of the span cannot be 4 in R3 space. It's impossible. How do you know whether we have a vector and it's a span of the other 2 vectors, or other 3 vectors, other 4 vectors? How do you know one vector is a span of other vectors? Well, to figure that out, all you have to do is you have to look for the combination, linear combination. So let's say we have a vector, a single vector x, and we want to see, is it a linear combination of the other 2 vectors? So a vector is in a span of the other vectors or not, it means the vector you have, is it a linear combination of the other 2 vectors?
Both A and B are non-zero?
Yes. All the scalar we have, they have to be non-zero. Otherwise, it doesn't make sense. So what you do is you multiply all the vectors you have by some constants, and then you see the vector you're looking for, is it a linear combination of the other 2? So you set this equation and you solve the matrix. When you solve the matrix, you have to see that the 2 constants you have, if they're non-zero or not. If they're non-zero, then it's inside your span. But if it's 0, that means something is wrong. It's not inside the span. So if you can find 2 coefficients that gives you this formula, or this formula works, then it is in the span. But if you cannot find such coefficients, then no. The new vector you have, it's not in the span. What does it mean? It means, let's say you are in R2 space. So R2 space, if you have 2 vectors, they're linearly independent, they cover the entire XY plane. So if you take any other vector in 2D, like you have x and vector with 2 rows, then that vector will definitely be in the span of the other 2. Why? Because in the span means however much area you cover in your vector space, the new vector, does it fall inside your area or not? The area you covered. It will fall inside the area you covered if it's a linear combination of the other vectors. But if it's not a linear combination of the other vectors, then it will be outside of the area you covered with your span. Okay? This is what it means. We're going to do examples. But right now, I'm just giving you all the information. The last thing is basis. Formal definition is a set of vectors form a basis for your vector space if and only if all those vectors are linearly independent and they span the entire vector space. Okay, span V means the entire vector space. It cannot cover only half or only small amount. It has to span or has to cover the entire space. So informal definition is that the basis is like the base or the foundation of your vector space. With those two or whatever, however many vector you have in your basis, those will create your entire vector space. And they are not unique. A vector space may have infinitely many bases. But whatever you have, those are the important foundation for your vector space. For example, if you're in R2, 1, 0, and 0, 1. So this means our x value, and this means the y value. So x and y, the unit vector x and y is the standard basis in xy plane. But they're not the only basis. 1, 1, and 1, -1 is another basis. Or -1, 1, and 1, 1 could be another basis. So you may have infinitely many bases, but whatever basis you have, they have to follow these two criteria. They have to be linearly independent, and they have to cover the entire space. So how can you check whether a set of vectors they actually form a basis for your vector space or not? Easy. All you have to do is to count how many independent vectors you have. If you have exactly n independent vectors in your Rn space, and it cannot have more or less, then they form a basis. Okay, so basis is the most strict one. It cannot have more, it cannot have less. It has to have exactly n many linearly independent vector in your set. So span and basis, they're like kind of opposite. Span can have more vector than necessary, but basis cannot have more vector or cannot have less vector. It has to have exactly n many vectors in your Rn space. So we need to have exactly 2 vectors in your set, 2 linearly independent vectors in your set to form a basis for R2. You need exactly 3 linearly independent vectors in R3 in your set to form a basis for your R3. So most strict one is the basis, which is similar to the span, but span can have more vectors than necessary, but basis cannot have more or less. Okay, so that's the background information we need to find the answers for all these questions. So we have a set of 10 questions. 2 in 2D, 3D, and I also had one in R4, but it was too big, so I just omitted that. So for these questions, you need to explain all of this, and this will be in the exam. Okay? Did you try them? In the email, I told you, please try them with your classmates. Did you guys try them? No? So it seems we don't have time. We're not going to cover all of them, but most likely we'll be able to finish everything in our next class. I mean, with my next class. So please watch the recording, whatever we can cover here from these questions. Plus, there are 2 more questions. And these 2 are the last thing we learned, whether the third vector or an extra vector is a span of the other vectors or not. So that's all for the rest of the chapter 3. Once you're done with this, you'll be done with the math portion. And then in our next class, I'm going to just give you some more theorem or more information about vector space. But math portion that's it.
Are those set questions too?
Exactly. So I'm going to make a review sheet about the weekend, and your exam will be 24. You remember that, right? November 24. So 2 weeks from today, not next week, 2 weeks. Shibu.
I was confused by the B question.
B? Okay. So let's do them. Let's see how much you can finish. Pen. Oh, let me take the attendance real quick. Oh, my head is hurting. Okay, today is 11:10. Brandon C. Joseph. Justin. Absent. Gibran. Shibu here. Michelle. Jack. Absent. Ashif. Here. Darius. Here. Winston. Abigail. Shane. Emily, not here today. Kanar, Christine, Edison, Maisha, probably absent. Brandon, yeah. Elvin, here. Shafal, absent. Alexander, here. Shitila, here. Wenchuan, here. And Kailun, here. Okay, so let's do them. We have two vectors in which space? R2. And the space dimension we can figure out from number of rows. We have 2 rows, that means we are in R2. So we have to check whether they're linearly independent or not. So 1. So when your 2 vectors are likely to be, all you have to do is check if one vector is a multiple of the other vector or not. It means, can you find a C so that if you multiply 2, 1, it will turn into 3, 2? Can you find such constant? Definitely not. In order to go from 1 to 2, you need to multiply the first vector by 2. But if you do that, you have to multiply 2 by 2. It should be 4, but you get 3. So C doesn't exist. C doesn't exist. Since C doesn't exist, so yes, they are linearly independent. The next question asks, how many linearly independent vectors we have? How many independent vectors we have? 2. We have 2 vectors and they're linearly independent. So number of linearly independent vectors is 2. Now question 3 says, do they span entire R2? Do they span entire R2? Yes. Span R2. Yes, because we have 2 linearly independent vector in R2. So if you have number of vectors is same as your dimension of your space, then span the entire space. So that tells us what is the dimension of the span. Dimension of the span. Dimension of the span means number of linearly independent vectors. So what is our dimension of the span? 2. So this question and this question, they're actually same. They're wording in different ways, but number of linearly independent vector means it's the dimension of your span. And now, based on all this information, What do you think about bases? Do they form a basis for the space? It means, do they cover the entire span? Sorry, entire vector space? Yes. Why? Because we have exactly two linearly independent vector in R2. So question 3 and question 5, they have the same reasoning, but the difference is this one has at least two linearly independent vector in R2, so they span. And basis says we don't care about at least, we have to have exactly two. We cannot have more or less.
Like while you're checking it, like one of the
Question?
the matchup, you just leave it and just
The answer is yes or no.
maybe continue on going.
Every question is independent of one another. They don't have any dependency. Now this one, how many vectors we have? 3 in which space? In R2. So one of them definitely has to be dependent. So that's we know. Since one of them is dependent, so we already know the answer for number 5. We need exactly 2 in R2, but we have 3 vectors in R3. So definitely they cannot form a basis. I should say does not form a basis. So before you even do anything, that's why looking at the number of vectors, you already know the answer for the last one. 3 vectors in R2, basis is not possible. Now let's see how many, or yeah, 1. 1 says, are all of these linearly independent? Definitely not, right? Because 3 vectors in R2 must have, no, I should write below here. 3 vectors in R2 must have 1 dependent vector. Well, good. Then how many independent vectors do you have? 1 or 2? Number of independent vectors. So how do you figure out that? How many independent vectors do you have? Do you have 1 or do you have 2? What do you do? Any idea? Shibu. You can do the echelon form. We have -2, 1, 1, 3, 2, 4 row echelon or reduced echelon form. One of them doesn't matter. Let's do it here. This page. -2, 1, 1, 3, 2, 4. Wait, but how do you know how many independent vectors you have? That will tell you whether they're independent or not. There's actually an easier way. And I taught you that in our last class. Anybody remembers? If you have more vectors than the dimension of the space, how do you figure out? One of the easiest methods is so let's say you're taking these two. 1, 3, 2, 4. Look for their determinants. What's the determinant of 1, 3, 2, 4? you do right diagonal, which is 4 minus left diagonal, which is 6. Is 4 minus 6 equals 0? No. That means definitely these two are linearly independent. And we can have only maximum 2 independent vectors in R2. And you already know them. If you have the determinant is not 0 for any 2 vectors or any 3 vectors, any 2 vectors in R2 or any 3 vectors in R3 or any 4 vectors in R4. If the determinant is not 0, that means you have that many independent vectors. So 2 vector give us a determinant not 0, they are independent. Okay.
Even if we take, for example, -2, 1, and 1, 3.
-2, 1, 1, 3. So this is -6 minus 1, which is not 0. But can you have 3 independent vectors in R2? No. So it doesn't matter which 2 vectors you take, as long as the determinant is not 0, you have 2 independent vectors. So all 3, they look like they're independent of one another individually, but one of them is a linear combination of the other 2. So individually, they're independent. But when you look at set-wise, they're not independent. They cannot be independent in R2. Okay, so if you want to find out how they're connected or how they're dependent, then you can look for your 2 constants that will give the third vector. But we are not looking for that here. We are looking for how many independent vectors we have. We have 2 independent vectors in R2. So that tells us question number 3. Do they span entire R2? We have 2 linearly independent vectors in R2. So do they span your R2? Yes. That tells us the 4th question. What is the dimension of your span? Means how many independent vectors you have? 2. Right? We don't need this much. And that's how you figure out. Now the next one is easy, so let me skip that. Let me go to something that looks a little bit harder. Which one looks harder to you guys? J. Okay, then let's go to J. What is the dimension of the space? R what? R4. How do you know? 4 rows. 1, 2, 3, 4. So we have only 3 vectors in R4. You already know the answer for 5. Do they form a basis? No. Why not? Dimension of the space. Good job. Does not form a basis. 3 vectors in R4. Something is wrong. Something is lacking. Something is missing. Okay, so let's see. Whatever we have, are they linearly independent? By looking at individually, they don't look like independent. They don't look like dependent, right? Because if you want to go from 1 to 2, you need to multiply the entire first column by 2, but then this one doesn't match. Or if you want to go from 1 to 9, you need to multiply the first column by 9, but then the rest doesn't match. If you want to go from 3 to 9, you have to multiply the second column by 3, but then this doesn't match. Like individually, the constant, we don't see any constant. We don't see their multiple of one another. So in this case, we have to see row echelon form. I forgot what row echelon form tells us. So we have 3 methods. Let me see which one makes sense. Determinant for square, we cannot use it because we don't have a square. Linear constant for 2 vectors, we don't have 2 vectors. Oh, the third one, find some constant so that the combination gives us all the constant to be 0. So basically you're solving for variables, solving for coefficients to figure out whether they're 0 or not. The C1, oh no, never mind, ABC. 8 times 1120, 1120. Actually, let me do it on the next page. It will take more space. Solution.
Does that mean if you could reduce to a row of 0?
Row of zeros.
That they are.
Because the last row is 0. So we have that 3 column and 3 coefficients. And if you can solve for them, as long as we don't have infinite solution, then if you have unique solution, then they're independent. What's the difference between unique solution? Like, how do you know they have unique solution or not? Like when you solve for variables, they have their unique numbers. For infinite, they don't have unique numbers. They depend on other variables. So if you can solve for each variable separately, then they are linearly independent. Even if you have the last entire row to be 0. So let's see real quick. Oh, we don't have time, but real quick. We have A1120 plus B2303 plus C19 negative 66. We want the result to be 0, 0, 0, 0. This is what we want. If you can solve for this ABC and we get all the ABC 0, then they're independent. Otherwise, they're not.
It can't be a multiscalar of 0.
No. ABC. All right. Right. We are looking for whether ABC, they all are 0 or not. If one of them is not 0, they're not independent. In order to be independent, they all have to be 0 because clearly the vectors are not 0. So how can the result be 0? If you multiply by the constant 0. Okay, so this is what's happening. We want the result to be 0. Clearly the vectors are not 0. If vectors are not 0, never mind. Let's see what happens. So we have 1120, 2303, 19 negative 66, 0, 0, 0, 0. If you reduce, then we want this to be 0. This is 2. We want this to be 0. So R2 is R2 minus R1, and R3 is R3 minus 2R1. So R3 minus 2R1. 2R1 means 2, 4, 2. And we have 2, 0, -6. So minus 2R1, minus, 0, -4, -8. So we get 1, 2, 1, 0. 1 minus 1, 0, 3 minus 2, 1, 9 minus 1 is 8. And then this one we get 0, -4, -8, 0, 0, 0, 0, 0. Oh, no, not 0, 0, 0. 0, 3. 0, 3, 6, 0. And then is -4. So we can divide. No, now we want this to be 0 and this to be 0. So R3 is R3 minus 2, not 2, sorry, 4R R3 minus 4R2, not minus, should be plus. And R4 is R4 minus 3R2. So R3 is 0, -4, this one. And if you subtract 4R2, means 0, 4 times 1, 4, 8 times 4 is 32. I get 0, 0, 24. And R4 minus 3R2. So R4 is 0, 3, 6, 0. 3 times 2, so 0, 3, 24. And when you subtract 3, right? 3. I get 0, 0, -18, 0. 1, 2, 1, 0, 0, 1, 8, 0. And we have 0, 0, 2, 24, 0. And this is 0, 0, -18, 0. We can get rid of this one. We can make this 0 if you combine with that. So we can make the entire pad, the fourth column 0. And then we can divide this by 24. So we get 1, 2, 1, 0, 0, 1, 8, 0, 0, 0, 1, 0, 0, 0, 0, 0. Since we have pivot points, so they have unique solution. We have x1, x2, x3. We have x3 is 0. So this one is telling us x2 plus 0 is 0. That tells us x2 is 0. This one is telling us x1 plus 0 plus 0 equals 0. So it means x1 is 0. Right? If x3 is 0, that means this is also 0. Because 0 times anything is 0. If x3 is 0, that tells us x3 is 0. If x2 is 0, x3 is 0, so multiply this by 0, multiply this by 0, you get x1 is 0. So we found all x1, x2, x3, they are 0, so they are linearly independent. x1 0, x2 0, x3 0 tells us v1, v2, and v3 all are linearly independent. Exactly. So we actually solve for the null space.
So what would happen if x1 had like 7?
Some other number, then they are not linearly independent. Okay, so they are linearly independent. Yes. That means the dimension of the span is 3, because we have 3 linearly independent. Do they span R4? Do they span R4? No, because to span R4, we need 4 independent vectors. But we have 3, so no. So 3, yes, and this is no. So in your exam, I'm going to give you something smaller so that you can easily find them. And most likely you don't need to use a reduced echelon form. But if you take linear algebra, the next class, the next level, then this knowledge will be helpful for you guys. Okay? So I'm going to do rest of the question with my other class. Please watch the recording. And if you have any question, if you don't understand anything solving those questions, we're going to discuss it in our next class. Have a good night.
Hey, Liz.
Let me actually pause this instead of pause. Okay, ready?
4.
How many were you able to do that?
I did the first.
You did up to I? Wonderful.
Hey,
Good job. And the last one is the hardest one.
I mean, I didn't do I.
Okay,
Do I?
no problem. So, do you remember all this information, guys? How do we know whether something is, whether a few vectors are linearly independent or not? How do you check them? Okay, if you have 2 vectors, only 2 vectors, how do you check whether they are linearly independent or not?
Scalar be multiplied to get from one to the other.
Good job. If one vector, if you multiply by a scalar, cancel to the other vector, then they are not linearly independent. And if you add 2 space, you can also look at the determinants. Let's review the materials, and then we are going to do the questions, all these questions. So, to check whether we have linearly independent vectors or not, if you have square matrix, like the number of vectors make a square matrix, all you have to do is find the determinant. If the determinant is not 0, they are linearly independent. But if you have 2 vectors in any space, your life is easy. All you have to do is check whether one vector is a multiple of, scalar multiple of the other vector. And if you cannot use either one of them, then the last hope is multiply all the vectors by a constant, not one constant, multiple constant, and find the solution of their homogeneous system of equations. So with all those vectors, multiply some constants and see if you solve the homogeneous system of equations, does it give us all the constant to be 0? If all the constant are 0, then they are linearly independent. But if one of the constant is not 0, then they're not linearly independent. And I'm going to post this on our Brightspace. I think I have logged in, so let me try if I can upload now. Can I? Yeah, probably I can. Before I forget, I should upload content, lecture notes, which I'm going to do modify later. But for now, at least you'll have some files to work with. Okay. Chapter 3, this one. It's the end, toward the end, the information I have now. Okay. So you don't have to take notes on everything here. They're available on Brightspace. Now span. Span means how much those vectors cover in the vector space. That's the informal definition. So if you have only one linearly independent vector in a vector space, it doesn't matter which space you are in. You may be in R2, R3, R4, R5, it doesn't matter. If you have one non-zero linearly independent vector, that vector can cover only a line in your vector space. The span of one vector geometrically gives us only a line. It covers only a line in the vector space. So one linearly independent vector is a line in R2. Again, I'm going to ask these questions as multiple choice. What's the geometric shape for the span of one vector in R2 or R3? What's the geometric shape for the span of two vectors? If you have two vectors, it doesn't matter, sorry, two non-zero vectors in your vector space, it doesn't matter which vector space you are in. The two independent vectors covers a plane, a two-dimensional plane, a 2D plane. It means if you're in XY plane, it covers the entire XY plane. If you have two non-zero linearly independent vectors. If you have three non-zero linearly independent vectors in R3, it covers the entire 3D space. Or if you're in Rn, it doesn't matter which space you are in, R4, R5, the three vectors can only cover 3D space. Okay? So span means how much you can cover using all the linear combination of the vectors you are given. Any questions so far? So how can we check whether a set of vectors is a spanning set for the space? It means how can we check the vectors given to us, do they cover the entire space or not? So if you have at least n linearly independent vector in Rn space, then you have the set of vectors, they cover the entire space, so they are a spanning set. The set of vectors have, if the set of vectors have individual vectors, at least, I should write at least okay. So if your set has at least n linearly independent vectors and they span your vector space, no, not span. Right. The set of vectors have at least n linearly independent vectors in Rn, and they span the entire Rn or the entire Rn. If your vectors can span your entire Rn, then yes, the set you have, the set is a spanning set. Otherwise, not a spanning set. If you have two linearly independent vectors in R2, then the set of vectors is a spanning set. If you have three linearly independent vectors in R3, then they are a spanning set. But if you have two linearly independent vectors in R3, they are not a spanning set. Means they do not span the entire R3. So each linearly independent vector, you can assume like there are variables. Two independent vectors in R2 means you need to have X and Y, both of them. If you don't have X and Y, so X gives you one vector, Y gives you another vector. If you have X and Y both vectors, then they can cover entire vector space. And they have to be independent. In R3, you have to have X, Y, and Z. So if you have three vectors, X, Y, and Z in R3, then they can span your entire R3 space, 3D space. So you need at least n many linearly independent vectors to span the entire space. If you can span the entire space, at least, you can have more. We don't care about the more, but we need at least n many independent vectors in your Rn space to cover the entire space. The dimension of the span means how many linearly independent vectors you have in your set. You may have one, you may have two, you may have three, you may have four, depending on your space. So how many independent vectors you have? That's the dimension of your span. Now let's say you have a set of vectors and you have a single vector. How can you figure out whether the single vector lies in the span of the other vectors? You can check easily by looking at if the single vector is a linear combination of the other two vectors or not. If the single vector is a linear combination of the other two vectors, then the single vector lies in the span of the other vectors. What does that mean? It means, let's say you have two vectors in R2, two linearly independent vectors. That means they cover your entire space. So if you take any extra vector and you want to see whether they are in the span of the two vectors or not, you can already know that the new vector will lie in the span of the other two vectors, because the other two vectors already cover the entire space. So the third vector is a linear combination of the other two vectors. So if you can figure out whether the third vector is a linear combination of the other vectors or not, then you can tell whether it's a linear, whether it is in the span of the other vectors or not. It means with the two vectors, whatever area or how much area you covered, the new vector, does it fall inside the area they covered? Or it falls outside the area they covered? If it falls inside the area they covered, that definitely has to be a linear combination of the vectors. If it falls outside of the area they covered, they cannot be a linear combination of the two vectors. And the last thing is a basis. Basis has similar properties as span. The difference is in span, we need at least n many linearly independent vectors, but to form a basis, they need exactly n many linearly independent vectors in Rn. It cannot have more vectors in your set. It cannot have less vectors in your set. You have to have exactly n independent vectors in Rn. So the dimension of your space has to be same as the dimension of your span. If they are same, then not span, sorry, dimension of your what? Yeah, dimension of the span is a linearly independent vector. So dimension of the span and dimension of your space, if they are same, then the set form a basis. What is basis? It's like the foundation of the space. The entire space can't be built upon those foundation, on those bases, and they are not unique. Like R2 doesn't have only one set of bases. It can have infinitely many sets of bases. The standard basis for R1, R2 is 1001. It means the X value and the Y value. If you have an X vector and a Y vector in R2, it's they create a spanning set for your R2. Also, they are the basis of your R2.
But if you had a third matrix, it wouldn't be the basis.
Third vector. They cannot be a basis. They will still span the space, but they will not be basis. Two. R2 can have exactly two. R3 can have exactly three. It cannot have more, it cannot have less. And that's all the background information you need to do, to find the answers for all these questions for all these vectors. And they'll be in the exam. I'm going to give at least two one for two R2, one for R3. At least for two to answer all these things. See here, I give you 10 of them. In the exam, I'm going to give you at least two. I can give more. It depends on the rest of the materials, how much I have. Plus, there is two more questions. They also will be in the exam. Andy, you miss a lot. All the background information, you miss them.
The exam is November 24th.
24, Monday, 2 weeks from today. Exactly 2 weeks from today. Your second exam. And I'm going to make a review sheet. So instead of giving you homework on the rest of the sections, I'm going to actually make a review sheet. So do the review sheet. Did anything break? No. Yeah. So why do you have the chair that far from the fan? Just put it near. Here. Exactly. That looks weird. What I was saying, I was saying something, right?
You give us, you wouldn't give us any homework.
Oh yeah, no more homework on chapter 3. Instead, I'm going to make a review sheet. Do all the questions with all the details. If you're missing any details, I'm not going to give you the points for that. Okay? So make sure show all the work for the review homework, and I'll try to post as soon as possible so that you have enough time to complete them. Okay? Any question before you start? So go ahead, try them for 3 more minutes or 4 more minutes, and then let me take the attendance, and then we'll start doing them. You know, today's supposed to be Veterans Day or something, right?
Yeah, tomorrow.
Tomorrow? But do you have school tomorrow?
What's
Hmm?
Veterans Day.
Veterans Day, yeah,
We
yeah.
have school, but like children do not.
All the offices are closed, like the governmental office is closed. Every school is closed. CUNY is open. Yeah. Yeah, that's right. We have only 2 days Thanksgiving break.
2 days.
2 days only, I think. Yeah. Only Thursday, Friday. When is it Thanksgiving? Thursday or Friday? Thursday. So people need to cook. They need to clean their house, right? When they're going to do it if they don't have the yeah.
Or you just have Thanksgiving on a Friday.
Do people do that?
Yeah, it's not that serious. Okay. Like to eat.
Hmm. You're done with what Friday?
Like, I'm doing the dinner on Friday.
With your family or friends? Both? In your house or in someone else's house? Are you going to help them or just eat the food? Which one?
I don't think I'm allowed in the kitchen. I'm sitting there, so.
Do you have to clean the house?
Yeah, I'll do whatever my mom asks, but she did. She's like it's like a war on Thanksgiving. It's like if I step in the kitchen when she's cooking, she'll cut my head off.
You are lucky.
Yeah.
Park, absent, not here yet. Jose here. Mehram. Kenyan here. Bora here. Indy here. Chuyan, not here. Jackson here. Christian here. Emmanuel here. Gregory was here.
Basis must be
Exactly that many independent vector as your space, vector space. Abid, not here. Origin, not here. Vlad, not here. Ethan, here. Elsa, here. Sometimes I wonder, like, are they still in the class or did they drop? I mean, I didn't see them drop the class, but they're never here. I'm going to grade that exam very harshly. I'm reminding you guys. If you're not here, don't expect to see any sympathy from me.
But Andy is a hack.
Well, no, you see, that's this weekend. I cheat sheet, yeah, I thought the exam was the 17th, but no, it's the 24th.
That's why you're so relieved.
The math exam for this class is the 24th.
24. 2 weeks from today.
Oh, nice. Oh, nice.
Mhm.
Does work out really nice.
Did I
Well,
say
it's gonna be
17
on the
before?
17th, but you moved it. You moved it. Yeah, cool. That's after Thanksgiving?
Before Thanksgiving. Thanksgiving is
Yeah.
26, 27. No, 27, 28. So yeah, it's right before. So we're going to have exam on 24, and then we're going to have an online class on 25,
Why?
on 26. Because next is Thanksgiving, so people,
Oh, you mean 26, right?
27 is the Thanksgiving, right?
Yeah, I don't have classes here on the 25th.
So 26 will be on Wednesday. So I'll make it online so that people who needs to clean their house, cook, they can do that. They don't have to be here.
Wait,
I don't have to go with the
that's so nice. Let me see this.
Yeah. We didn't celebrate, but we know like how much headache is that to clean the house. I hate it. Yeah. Instead of Thanksgiving, we have Eid. It's like Christmas. So to clean the house, cook and everything. I hate that. I hate cleaning. 2 more minutes, okay, and then you're going to do them together. You like cleaning? Do you do the normal cleaning or deep cleaning? Normal ones? In our house, they mostly do kind of deep cleaning. Like they have to clean everything, scrub everything. Yeah, I hate that. What is happening? Emmanuel, no phone. Please, no phone. You have not done it all 10 of them, right?
Yeah.
Really? Show me your work. Don't tell me you did them in your head. That is not acceptable. And also in your review homework, make sure show me all the details work. Do not tell me I did it in my head. Okay?
Look at me.
Also, Kenyan, please show all the work.
If you don't know how.
At least tell me I don't know how. Do not just give me the answer. And actually, you should, if you watch the recording, you'll know them. You'll know how to do them. Because every questions you see in the review sheet, we went over in class. Maybe not the same question, but a very similar question. So whatever you don't know, go watch the recording. And if you don't want to see the recording, search on Google how to solve this. Not what's the answer, how to solve this. Okay.
Yeah, what I put back like the matrix solution, but it's like rewrite it.
Then ask for solution. Ask, how do we solve this matrix? How? That's the keyword, how. So they'll tell you step by step. Read all the steps. And if you don't understand, ask them. You know, did you see nowadays, if you type anything on Google, AI comes first, with whom we can just talk. I actually learned many things from AI about these things. Like I had a question. Is basis really means the foundation of the space? He said, yeah, it's a good way of thinking. I was like, good.
What makes sense in that matrix function?
Probably. I mean, the information, I search for the information, like, is this true? Is that false? Or what does this mean? Like, what is basis? Can you think basis as this way? It's like, yeah, gather the information. And then it's better to check because sometimes they give wrong information. My sister searched AI on Google. Do we have off on Veterans Day? It says, yes, everything is closed on Veterans Day. So my sister was like, why are you lying to me? The youth schools should be closed. It's like, I'm not lying. Like CUNY doesn't have off. He said, look, here it says on Google. AI said CUNY is off. Like, really? So do not trust AI. It doesn't have any brain like us. Okay, start. Are you doing something?
I was finishing, yeah.
So let's do it here. The first one, we have 2, 1, 3, 2. Are they linearly independent?
Yeah.
How do you know? This is correct, but how do you know?
And the scalar multiple of the first one is not equal.
Good job. You cannot multiply the first vector with anything that will produce the second vector. So they're independent. So how many independent vectors do we have here? 2. And what is our space? The dimension of our space? R2. So 2 linearly independent vectors in R2. Is it a spanning set? Yes.
So because with scalar, if we multiply it with the other, like, that's all.
For example, if you want to go from 1 to 2, you need to multiply this vector by 2, right? So 2 times 1 is 2. But what is 2 times 2?
3.
Should
No.
be 4. But do you have 4?
No,
So they cannot multiply.
it has to be like square.
Not square, like all the numbers have to match when you multiply.
When you just did, the answer is 1 or the answer is 2?
Which one are you talking about?
The one where you said that 1 times 2 is 2, but 2 times 2 is not 3.
If you want to see whether they're independent or not, you just looking at this vector times some number, will it give us this vector?
Okay.
So if you want to go from 1 to 2, you need to multiply this vector by 2, right? So 2 times 1 is 2. 2 times 2 should be 4, but you don't have 4.
That means 1 is then.
It means the 2 vectors you have, they're not dependent. They are independent.
They're linearly independent.
They are linearly independent.
So how do you answer number 2?
2 says, how many independent vectors you have? How many vectors you have here? And they both are independent. So how many independent vectors you have?
Oh, so they're both independent because 1 was independent? Like 1 was.
They both are independent because one vector cannot by multiply with something to get the other vector.
Or you can also think about it like you can't go from the second vector to go to the first, or you can't go to the first from the first vector to the second.
You cannot go from one vector to another vector. It's not possible. That means both of them are independent. And we have only 2 vectors, so we have 2. And since you have 2 vectors in R2, so do they span the entire space R2?
Yes.
Yes. So what's the dimension of your span?
But
Means 2, only 2. How many independent
Oh.
vectors do you have?
Oh,
Only 2. So you have exactly 2 linearly independent vectors in R2. Do they form a basis for R2?
yeah.
Yes. Good job. We did that. We are able to answer A perfectly. Now for B, the answer for the 5th question is automatically given. How many vectors do we have? In which space? R2. So do they form a basis? No. In order to be a basis, you need exactly n many vectors, linearly independent vectors in RF. So in R2 space, you need exactly 2 independent vectors. We don't have exactly 2, we have 3 vectors. So definitely they do not form a basis. So 5th question is automatically given to us, automatically. Now the first one, the 3 vectors you see, are they linearly independent?
Yes.
All three?
Which one?
No, C is not. It's not.
From
Oh,
A,
way up.
are they linearly independent?
Yeah, yes, they are.
yes, they are.
All three, they are independent of one another?
No. Yes.
How many independent vectors you can have in Rn?
Rn.
How many maximum number of independent vectors?
One and three.
In n space, you can have n independent vectors. For example, in an xy plane, can you draw xyz?
Wait, in the Rn space?
It means
So is it?
You can have, no, because Rn is the, like, N is how many, you count, how many, like,
how
down.
many rows we have?
But
The N
then,
is
but
right
then,
about that.
we're talking about vectors, like infinite, so the answer is not N, it's infinite.
No, we're talking about in xy plane, how many variables you're allowed to have? Two. And both of them are independent. X is independent of Y. So R2 can have only two maximum independent vectors. In R3, how many independent vectors you're allowed to have? Three, X, Y, Z. You cannot draw more than X, Y, Z in your R3 space. So you have three vectors in R2. Are all of them are independent? Definitely not. One of them must be a dependent. It means one of them has to be a multiple of a linear combination of the other two.
Okay.
One of them, which one? We don't know. But one of them has to be a linear combination of the other two. Because we have X and Y. Okay, X and Y value. So you can have 100 variables, 100 vectors, no problem. But you can have only two independent, maximum independent two.
This is for B, we're saying
B.
B, and then they,
So question number one, are they linearly independent? Of course not. What did I just tell you? One of them must be a dependent on the other two. So all three, they are not independent.
so that's, the answer for two is still, is two.
How do you know? Bora, question.
So my question was, okay, so because it's R2, but there's three vectors, that automatically means one of them has to be dependent?
Exactly. Because two can have only two independent, maximum two independent vectors. You can think of it as X and Y,
R2 means,
XY plane,
so like two rows?
two rows.
Okay.
So one of them is X, one of them is Z. So like one of them is Y. So you can have X vector and Y vector. The other vector is a combination of X and Y. Which one, we don't know. But one of them is definitely dependent. So how do you know how many independent we have? Do you have one or two independent vectors? How do you know?
You said at least, oh, you said at least,
I said at least. Not at least, I said at most.
because none of them are like, none of them are
If
dependent.
you have only two, then you can use the constant multiples.
This is
For
just-
three, you cannot use that method.
This is just a system of equations.
System of equations, or you can just take any two vectors, look at their determinants. Individually, they are not multiple of one another, right? So the multiple method doesn't work. But we have two other methods. One is determinant method and one is the constant method. Take any two vectors and look at their determinant. If the determinant is not zero, that means the two vectors you took, they are independent. So take any two. Let's say you're taking this one and this one.
So -2 times 3 is -6.
Six
And then 1.
minus one.
Minus 1 is
Is it zero? No.
-7.
How about these two? 1 and 4
4.
minus 3 times 2.
-2.
Is it zero? No.
No.
So two vectors are definitely independent
2. Okay.
because the determinant of two vectors is not zero. That means those two vectors independent. So here, this is independent of this one. This is independent of this one. But one of them is a combination of the other two. a multiple, a constant multiple of other two, a linear combination. So the answer for 2 is 2. We have 2 independent vectors. How do you know? Because the determinant of 2 vectors is not 0. So they produce 2 independent vectors. So you found that you have 2 independent vectors in R2. So do they span entire R2? Yes. So what's the dimension of your span? Means how many independent vectors you have? 2.
But wait,
So-
we just tested the different combinations of these 3 vectors.
Individually.
Taking the determinant.
Mhm.
We didn't find any of them that equal 0.
Mhm.
And how-
The
how
2
do we
vectors you
conclude
got,
that-
they're independent.
How do we conclude from that? We have it in,
How do you know whether we have 2 or 3 independent vectors?
now what have we taken away from doing the determinant?
Determinant is telling you the 2 vectors you're working with, do they have any relationship or not? Do they have any connection or not?
And if the determinant is not 0.
They do not have any connection.
So what?
do not have any
like,
relation.
Finding that
That means they're independent. They don't have any connection.
but we.
For
found out
example,
that
this
all
one,
three-
pick the determinant of these 2.
Right.
What's the
but-
determinant of these 2?
Oh, wait, can we just stay at B for a second? Sorry, because if we.
This is what I'm saying, like, if you look at this one, what's the determinant?
16 minus 16.
0. So are they independent?
Yeah.
Huh?
No.
They're not. Same scenario is here. Take any 2. If determinant is not 0, they're independent. If determinant is 0, they're not independent.
It's not 0, they're dependent.
Not 0 means independent. Not 0 means good thing. They're independent. They don't have any relation.
We found that all three, sorry. go.
You can take any 2. I just tested all 3, but you can take only 2. Only 2. And you can take only 2 and then stop. Why? Because you're in R2 space.
So did we prove that all 3 are independent from each other? Or you
No,
saying,
we
if
proved
you're
that.
saying at the same time, that's impossible?
This is what I'm saying. Maybe you like to take the first 2.
Yeah.
Maybe Andy like to take the last 2. Maybe Bora like to take the first
It
one and the
doesn't
third
matter.
one.
You're saying
It doesn't
that-
matter which 2 you take.
Yeah.
If the determinant is not 0, those 2 are independent. And if you have 2 independent in R2, you already found the answer. You cannot have more than 2.
Even as theoretical as it might be.
Even though they all are independent of one another, if you look at them, they look like they're independent of one another, but actually they are not. For example, 1 and 2, are they independent of one another? Let's say they don't have any connection.
Yeah,
No, right? Because 1 and 2, they are different. But 3 is actually 2 and 3, they are independent of one another. 2 and 3, 2 is 2, 3 is 3. 1 and 3, they are independent of one another, right? 1 and 1, 3 is 3. But can you write 3 as 1 plus 2?
Yeah.
See? Even though individually they are different from one another. But see, you can write 3 as a combination of 1 and 2. Or you can write 2 as a combination of 3 and 1.
so being dependent doesn't necessarily just mean that it's a scalar,
Multiples, right?
it's a scalar, it could be more.
It's a, what they call a linear combination. Means you multiply by a constant and then add with other vectors.
Like using the Gaussian, the row operations, they could have gotten one of those 3 matrices.
If you use raw operation and then you can solve for each constant separately, they are independent. Right? No, if you cannot solve them, then they are not independent. Okay, main thing. R2 can have maximum 2 vectors.
Yeah.
So take any 2, it doesn't matter which format you take. Take any 2 and then be done with that.
Yeah,
And if you get the 2 of them and say 0, then take another 2. Okay?
Right.
Keep trying until you see if at least you get any 2 pairs gives you determinant not 0. If you have at least 2 of them, that means they are independent in R2. So they span the entire set. Now C, it's very easy, right?
dependent.
They are dependent. Good. But at least how many independent?
Zero.
It cannot have zero. 0 times nothing is going to give it to 4. One of them is independent. Maybe the first one, maybe the second one, maybe the first one, the second one, it doesn't matter. But one is a combination of the other one. So that one is the independent one. So what's the dimension of his span?
1.
1. But the question is, do they span entire space?
No.
No. With one vector, how much you span or what do you span?
R1.
With one vector, you can span just a line.
Oh, yeah.
So if you have an entire big space, that one vector going to give you only a line that goes to 0, 0. Okay, so do they form a basis? No, we don't have two independent vectors. Okay, so we answered all 5, A, B, C. D. Which space we are in? R2, R3, R4, R3, because we have 3 rows. So that means we know the answer for the 5th one automatically.
Yeah.
Is it a basis?
No.
We need exactly 3 in R3. We don't have them. So we go back to 1. The 2 vectors we have, are they independent of one another?
Yes.
Yes. For 2 vectors, our life is easy. All you have to see is if one vector is a multiple of the other vector. For example, here, you can never go from 1 to 0. You cannot multiply with 1 with anything, it turns into 0. It's impossible. So these 2 vectors are independent. So what's the dimension of his span? 2. Now 2 independent vectors in R3. Do they span entire space? We need X, Y, Z. We have only X and Y. The Z vector is missing. We answered all 4, right? All 5.
Wait, what was 3 for me?
At this spanning set for R3 means do they cover entire R3?
Oh, no.
No. We need 3 independent vectors to cover R3. 2 vectors. How much 2 vectors cover?
2.
XY plane, 2-dimensional plane. So in XYZ plane, in 3D, they only cover a plane, XY plane, 2-dimensional plane. They do not cover the entire 3D space. It's like it's a sheet. With 2 vectors, 2 independent vectors, you get only a sheet on 3D space. Okay, so D is done. Number 4, what's the dimension of the span? Means how many independent vectors you have?
2.
2.
Or 2.
And they do not form a basis because the third independent vector is missing.
You need 3 vectors for a basis.
Exactly 3 linearly independent. Just any 3 is not going to work. They have to be
Linear.
independent.
So 3 linear independent?
3 linearly independent vector. If you have in R3, then they form a basis. And they span the entire vector space. Now for E, we need to do work. So let's go. E. Let me get it here and start. So which space we are in? R2, R3, R4? R3. And how many vectors we have? 3. So 3 vectors in R3. How do we check whether they're independent or not?
Take 2.
You cannot take the determinant of an square matrix.
Take the determinant of
Entire 3. Linearly independent. So we need to look at the determinant. -3, -6, -1, 2, 5, 1, 8, 14, 2. And there are many ways to find them. My favorite method of 3x3 is rewrite the first and second column, -3, -6, -1, 2, 5, 1. And look at their diagonals. How much we get from this diagonal? -30 plus the next diagonal, 2, 14, and -1. So it should be minus -28. The last diagonal, 8, -6, and 1. -48. So these are the right diagonals. And then you're going to subtract the left diagonals. So this is the fast left diagonal. What do you get? 8 times 5 times -10, -1. So we're subtracting, okay? -40. Then the next diagonal is -3 times 14 times 1. 14 times 2 is 28. So 28 plus another 14, 42. And we are subtracting, is it positive 42 or negative 42? Negative. -42. And then we have the last one, 2, 6, and 2. -24. So basically, all these numbers turn into +40, +42, +24. What do you get? Do the math. Zero? Our determinant is 0. So are they independent? No. Because determinant of this is 0. That means one of them, at least one of them is a combination of the other one. So now you have to check. Well, all three are not independent, but how many independent we have? 1, 2, 1 or 2? How do you know it's 2?
Maybe because, like what you said earlier, if we can't find or am I going the right way?
If you take any two vectors, are they multiple of one another?
Yeah. And if we can't get anyone that's not even, but you know what I mean. If we can't find two of those vectors that match.
So if you have only two vectors you're looking for, your life is easy. All you have to do is check whether one of them is a multiple of the other one or not.
Multiple, yeah.
So if you look at the first two, can you multiply the first vector by something that will turn into the second vector? That means the first two, at least two of them are independent.
Yeah.
We definitely know that all three are not independent. Why not? Because the determinant is 0. So we just figure out that at least two are independent because they are not multiple of one another. So 2, number of independent vectors is 2.
Which one is it?
Any two.
What question is?
E.
The multiple of one.
If you have two vectors, just look at the multiples. Can you multiply one vector by something and it will become the second vector? Okay, so they are not linearly independent, but if you figure out that at least two of them are independent, the next question is asking, do they span entire R3? No. 4 is asking, well, what is the dimension of his span? 2. Because that's the number of independent vectors. And the last one is easy, right? No, why not?
Because
Only 2, so we do not have 3. We need exactly 3 linearly independent vector to form a basis for R3. Who is lost? Anyone? Little bit?
I'll get there.
That's why I tell of this. Think about the next one. Now try this one actually by yourself, because you already did 3. One of them with 3 dimension. Now try this one and see which part is confusing for you. Do you want to see the questions, Bora? Which question? You have them? Okay.
But these kind, we can't find independent.
You just have to take the determinant. Inspection, you can take the determinant using inspection, but inspection help you if you have more zeros. This doesn't have any zeros. Hmm?
You'll have to take it and find out.
If you have 3, you must need determinant, because it's square matrix 3 by 3. The third one is asking, do the span 3. The next one is asking, what's the dimension of the span? And the last one is asking for the basis. To find the determinant. And see the method I use? That is one of the good methods. It's only 3 by 3, it's not hard. 4 by 4 is hard because this method doesn't work on 4 by 4.
Well, that's like just multiply and diagonal.
So first you write down your matrix. -2, not -2, sorry. 2, 1, -1, -4, 3, 2, 1, 3, 1, 4. You write down your original matrix. And then you copy the first 2 column next to the third column. So 2, -1, -4, 3, 2, 1. And then you keep finding the diagonals. You start with the right diagonal. Means you start from the left, go down. So it's the right. So start from the top, go down. This is your first diagonal. The next one starts from the top, go down. That's the next diagonal. Start from the top, go down. That's the next diagonal. So all the right diagonal, you're going to add them. And you take the left ones. Start from the right, go down on the left. You're going to subtract that amount. You multiply this, you subtract. You multiply them, you subtract. Bora, question?
Yeah, so you know how like for E, when we did the right there, it equals 0 on the left side? So if it doesn't equal 0, that means that all 3 are the map.
That all 3 are independent. Two to 4, 4 times 4 is 16. 4 -3 is -12. 1 is -3. And then subtracting 4 plus 8, this is 24. 2 times 1 is 2. 3 -12. So that's -12 minus 2, -24.
When I do this, the other method, like plus minus plus, and then I move over by column to column, right? And then with this, is it negative positive? Or is it?
No, you take this number and multiply by the determinant of that.
Or which, the 2?
So you crossed out 2 here, right?
Yeah,
So you take this number with the plus
for
sign.
all three of them.
No, for this one.
Okay.
Plus 2 times determinant of that. Minus -1,
Mm-hmm.
and then the next one, determinant of the next.
Oh,
Too
for
much
the,
work.
look at the, what I did for the next one.
So the next one you cancel out, or you're going column wise,
Mm-hmm.
row wise, sorry. So that means if,
Oh, 2, 3, 2,
if
3.
you're going row wise, then why should it plus minus plus
Oh,
one?
yeah, yeah, okay.
It should be on the top. So +2 times determinant of this 2 by 2.
Mm-hmm.
-3
Mm-hmm.
times the determinant of this. Then +3 times determinant of that.
Mhm.
And then you combine all the results. +12 minus 12 cancel. It's definitely not 0. Right?
No, no.
Andy, what happened? Henyan, how are you doing? Did you find the determinant? Or stuck? Did you find it? How much is the determinant? 9? Probably, but it's definitely not 0, right? So how many independent vectors do you have? Good, you answered it fast. We have 3, so 3 independent vectors. So the answer for this one is yes. All 3 we have, they are independent. Since we have 3 independent vectors in R3, so they span the entire XYZ plane.
The dimension.
Mm-hmm. The dimension means how many independent vectors you have. The hardest part is 1 and 2. If 1 is yes, our life is easy. But if 1 is no, then you have to find out how many independent vectors. Any question on this one? Okay. One more. Or you can skip it and then you can go for the next one. Yeah, next one is easier. We have 2, 1, -2, -2, -1, 2, 4, 2, 4.
So, 1 and 3 are not, or they're dependent on each other.
So
Times 1.
they are not, all 3 are not linearly independent. Now it's time to figure out, good job, but how many? How many independent vectors do we have? 1 or 2? 2, how do you know?
If 1 and 3 are.
Let's compare at least 2 of them. Are they independent of one another?
Of 3. The answer is 3.
Are they independent? It means, can you multiply 2, 1, -2 by something? Yep, if you multiply this by -1, you'll get -2, -1, 2. So these 2 are not independent. Okay, now let's check these 2.
Yeah. -2 gets you there.
So V2 not independent of V3. How about V1 and V3? They are or they are not? V2 not independent of V3. So how many independent vectors you have?
3 of 0.
It can never have 0.
Oh, yeah.
One vector is the main one. The other 2 are thus multiples of that one. So So question number 2. How many independent vectors? 1. Every space has at least one vector, independent vector. At least one. You can never have 0. Even if you have a 0 vector, that's still a 1 vector, okay? So you can never have a 0 vector in any space. Every vector space is non-empty. Remember that in order to be a vector space, one of the condition is it cannot be empty. So every vector space is non-empty. That means whatever is given to you, one of them is there. It's independent. So one independent vector. Okay. Question number 3. It says, do they span? Of course not. We don't have enough. No, do not span. Do not span. Well, good job. But then what's the dimension of a span? 1. This one and this one are the same thing. Another easiest one. Do they form a basis for R3?
No.
We do not have enough vectors to form a basis. Okay, 8i.
With this one, we don't find determinant, right?
We started with determinant. No, we didn't start with determinant. Why not? Because we can see clearly that the second vector is a multiples of the other vector. First one.
So in this case, they were all, for the multiplication that we're doing, they all like, I guess, passed, you could say? Like,
So V3 is, no, let's do V2. V2 is -1 V1.
Yeah.
And V3 is 2, twice V1, right? So V2 and V3 are dependent of V1. So which one is independent? V1 is V1. V1 is V1, that's the independent one. The other two depends on V2, so you only one independent vector.
but let's say if, one of them, like, let's say V1 and V3 were dependent, but V2 wasn't, of either one.
Like this example, not this one. The last one, this example, right?
No, because none of these are dependent to each other though.
They are, but you don't see them directly. So this one you can see.
No, if you could see it, but it's only for two of them. One of them does not, like, it doesn't even add up.
For example, you may have 1, 2, 3, and then 4, 5, 6, and then you may have 5, 7, 9. Something like this, right?
No, none of them would multiply, none of them will be dependent. Like,
If you add this, do you get that? If you add this, do you get that? If you add this, do you get that? This is 3. You see, 2 of them are independent because they do not have any connection.
Yeah.
But the third one, even though you don't see it, it's visible. I mean, it's kind of visible. The same thing here, all 3 are visible. So you could do everything without doing any determinant. But here, you can start with determinant if you don't see them. But if you already see that one of them is dependent, do not waste your time on dependent because it doesn't work. Just look for any combination.
okay.
So we still didn't do a few of them. Try them home, especially the last one, J. Try it at home. And then try these two also, the last two. Okay, definitely try these two at home. And then whatever we didn't do from A to J, try them at home. If you have any question, we're going to discuss them in our next class. Have a good night. Be safe.
So I was trying to say it's something like this. Let's say if it was like 2, 4, 6, and this was like 4, 8, 12, and then this one's like 3, -1, 2. That's something random. So these two multiply, like, do the multiplication together, so these two are independent, but then this one doesn't add up to any of them, so would this still just be one independent?
No, because one of them is independent here, and the other one is dependent on that function. That
Okay.
will be vector.
This one is also independent.
Here's two vectors.
Ah, I see.
So now you look at is, well, these two are dependent, so one of them is independent. Then you compare these two. Then you multiply this by something so you can get that. That means these two are independent.
Okay,
So you're looking for, if you have at least two, that means you're done.
but this means that there's two independent, not three.
Two.
Okay, two, okay. Thank you.
Yeah, you're late. Car. Mhm.
I didn't come to class last 2 days.